Let's now talk about group by. Group by is probably one of the most common operations that you'll see called in pandas, and in fact, it will have the most varied performance of everything you'll encounter in pandas. You have everything from group by apply, ag, and transform. And just for everyone's reference, I want to cover what we're talking about here. Pandas group by operations, or all data table group by operations, are divided into 3 steps: split, apply, combine. We pay for these, each at their own individual cases. To split a data frame into multiple subframes or subtables, we need to have some notion, right? What are the groups? And if we're thinking about a pandas data frame, we're thinking about the underlying, right, NumPy representation, if it's backed by an ND array, then we can think, are the groups contiguous? Are the groups shuffled? Because if they are contiguous, I can use a series of slices or a series of views to just grab some access into that ND array, and views are super cheap. But if the groups are all shuffled, well, then I'm going to have to use a Boolean filter in order to grab, right, all of those slices of the data frame. And a Boolean filter in NumPy means I'm making a copy, which is a little bit more expensive. So I would have to copy data around there. So that's our split step. In our apply step, right, we're going to be applying some function. Usually, right, in pandas world, we're going to be applying some arbitrary user-defined function. This will always be slow. And so if you can avoid a user-defined function, if you can avoid a lambda inside of your group by apply or your group by.ag or even your group by.transform, it's going to be to your best benefit. And there's some tricks to altering your thinking about how to avoid those user-defined functions with those methods. Our final step is going to be combine. We take all of those constituent parts, right? We split, we applied some function to each of those split pieces, and then we combine them back into a single data frame. There is a price to consider when recombining. So let's talk about .apply first. We can take our data frame, which has some number of groups. In this case, these groups will be ordered. Then we have 2 columns of values. Say I want to grab the mean of the sum of these 2 columns. Well, I can do a group by apply, and apply is the only method in pandas, or the only group by method in pandas, where you actually have access to the entire underlying data frame. And so I can do something like this. I can pass a lambda, I can grab the column value 1 from each group, and I can grab value 2 from each group, I can add them, and then I can calculate the mean. Now, this is going to be quite slow overall. And it's going to be quite slow because I'm passing this user-defined function. Pandas can't see through this lambda. It has no idea what I'm trying to do. And so it can trigger maybe 1 fast path, but it can't trigger very many fast paths. Instead, what I need to start thinking about is not kind of the Python sense where I want to do all the work inside one loop. I want to use the vectorized loops that pandas and NumPy have to offer, especially if I know it's going to be hitting the NumPy computation layer. And so what I'll do here is I'll create a temporary column. You can think that the addition of these 2 groups, or these 2 columns, this can be done inside the group by, but it can also be done outside the group by. And by doing it outside the group by, I'm making a temporary column. I'm actually going to be hitting the NumPy computation layer here just by adding 2 columns like this. I am passing a lambda, but this lambda is akin to a pipe, right? The dot assign is going to be the same thing as a pipe here. So I'm just calling this lambda 1 time. But I'm going to be evaluating, right, column 1 plus column 2. Then I can perform my group by, and then I can take the mean of that temporary column. And we can see I get the same output, but the performance difference is crazy. And so we always want to think in terms of vectorized operations and what you can do outside of the group by first, and then perform as little as you can within the group by as possible, especially if you can reduce your call to a built-in for pandas group by method, or one of those built-in string methods, right? If I do .ag with mean, or if I can call it directly .mean. But as soon as you do something with a lambda on a ag, apply, transform group by, you're going to be hitting the slow paths. Let's talk about ag now. Ag behaves a little bit differently than .apply. .apply, you have access to the whole frame. Ag can only be called on 1 column at a time unless you pass it to the NumPy backend or the NumPy engine. We don't have examples with the NumPy engine here today, but just know that you can use NumPy to speed up your computations. Now, the difference here in these approaches, I'm going to call ag with a lambda, and for every single group, I'm going to call .mean on it. I'm going to call ag with sum on it, I'm going to call ag with my statistics.mean, and let's look at the differences here. Calling a lambda onto group by, fairly slow. Calling the mean from the statistics module, I'd say is kind of slow. I mean, it's more similar to the lambda than it is to the sum. And we have to think, this is Python sum, right? I didn't do from NumPy import sum. This is just the built-in Python sum. What's going on here? Well, we have to think about what is pandas going to intercept. When I pass in a callable, pandas will do its best to try and find some NumPy ufunc that's similar. And so when I pass in the built-in sum method, pandas actually says, oh, they passed in sum. I'm just going to use the NumPy sum and use any fast path that I can for the NumPy sum since that's a ufunc. The statistics.mean, well, pandas hasn't registered this to map to the numpy.mean function. And so we actually end up calling the tried and true statistics.mean on every single column or in every single group of that column. If we actually perform, right, say I do a lambda g here and call sum directly on g, we do see that our performance decreases, right, especially since we're not triggering that fast path anymore. You can see a times 10 difference there. If we just stick with the tried and true group by groups.mean or pass the string in, pandas will trigger its fast paths. And my general rule of thumb is this: always use the group by the grouper object or the group by object. Use the methods attached to that. Try to avoid .apply.ag and passing in your own callable. Or if you're going to use .ag or .apply, right, pass in a string. This will trigger, if you pass in a string, this will trigger pandas fast paths every single time. And if you use, right, the direct method, then you'll also be hitting fast paths. Here, you introduce some ambiguity as to whether you're able to hit a fast path or not. And so you can always rely on these approaches to trigger fast paths. Talk about our last approach here for pandas group by, transform. For pandas group by transform, we are going to be visiting, again, every single column and every single group. Now, transform has a couple of differences to it in its behavior to ag and apply. Transform has some more explicit or less abstracted, I should say, fast path detection. And what it's trying to do is trying to assess whether this is a NumPy ufunc that can operate across all of my data at once, or if it's some odd user-defined function that I can't do really much with. And so this isn't the end of the story. There is much more to this on how pandas will actually call these things and implement them. But what I want to share with you is this. The group by object, as of pandas 2.02, has a hidden method or a hidden method here, private method I could say, called define paths. This assesses whether, or this will actually wrap the function that I pass into it. In this case, it's going to grab the mean function that's attached to a series, and it's going to wrap it two ways. It's going to first say that this is the fast application. It's going to call a function on the group, and it's just going to pass in whatever arguments I forward into it. The slow application is calling a group.apply, right? Meaning this lambda is going to visit every single element within a given group here. Now, when I run this and I pass in, right, I get my fast and slow paths from the define paths method, well, we can grab our next group. We can grab the first group out of this group by object, and then we can have pandas decide, are you going to use the fast, quote unquote, fast path, or are you going to use the slow application here for this given group? And we can see that when I use mean as a string, we take a fast path. Now, when I use a lambda with .mean, we also are taking a fast path, but we don't get the same performance. And the story is this. The performance difference that we would see using the string mean versus a lambda with x.mean, we end up, right, applying this lambda on every single group that we see inside of this transform call. And then that Python function call ends up calling, right, the siphonized .mean implementation. Whereas this mean using the string, we can skip that Python function call altogether. And so we do see a performance difference, but we are seeing that we are still triggering some fast paths that pandas has to offer. Lastly, we can do something incredibly arbitrary, and we can essentially have a return type that pandas is like, wait, what do you want me to do with this return type? You know what, I'm just going to take the slow path. I don't think we can call this function at the group level. And so when we use this approach, right, we see that we end up taking the slow path because pandas has decided to. Now, if we look at the timing of these two paths here, we can see that the top one where I use the string mean is going to be faster than using the lambda because, right, it's a little bit more transparent as to what it's doing, and it will actually trigger some more pandas fast paths. So when using apply, ag, and transform, always use those string implementations because they will trigger as many pandas fast paths as possible. It is a very convenient level of indirection that pandas has exposed to us. So we don't have to guess, well, if I pass numpy.mean in, is that going to be fast? If you stick with the methods that are on the group by object or with passing strings in, we know that pandas has optimized implementations of those. And so we can always rely on them. Now let's talk about the final step of our group by, the combine. When we want to perform right or split, apply, combine, this is our final step. And we do see that there is a cost to it. The more groups that I have, the longer the combination step will take. But let's take a look at how much longer. In this example, I am sleeping for 1/10,000th of a second per group. And in the next example, I am sleeping right for 1,000 times that. So for just under 1 second per group here. And so the difference between here is that this first test has 10,000 groups in it, and the second test has 10 groups in it. So I've offset the sleeps so that they should take the same amount of time, and the only difference in timing between these two will show itself when we are on that last step, that combination step. You can see that this combination here is costing me a good amount of time. With 10,000 parts to combine, we need to allocate a lot of brand new memory space in order to fill in all those parts. And then we need to iterate over those at the Python level and start filling in those buffers that we've allocated. With just 10 groups, it's a much faster, much cheaper operation. And so we do see that every single part of this operation, split, apply, to combine, all take time. And there are ways that we can speed each of these up, or unfortunately, there are ways that we can slow them down. The last thing that I want to share with you is about that split step. The sortedness of your groups does in fact matter. In this example, the top example, I have groups that have been randomly shuffled, whereas in the second example, I have groups that are sorted. So I'll label these for you, shuffled like this, and then sorted groups here. As I hinted at earlier, whenever pandas is performing a group by operation on sorted data, we do see a slight benefit in performance. Now we have a lot of groups here. And so you can imagine, right, the number of copies that I need to make if I'm using a Boolean indexing versus the number of views that I can just simply grab by using contiguous slices is actually going to result in a performance difference in this code. And so here I am using, right, the very fast vectorized, right, .mean application here. But the thing that we want to be wary of is all this was just a pre-sort. And so if you sort your data while you're loading, if that's a step, you're actually going to see not just a performance increase to grouped operations, but to a lot of other things that pandas has to offer. So if your data does have a natural sorting to it, I would always recommend that you pre-sort your data because you're going to see performance gains over a lot of your operations. Let's quickly talk about NumPy. Is it actually faster? Do we want to drop to the NumPy level? Well, it turns out we often do. NumPy will have better performance than pandas. However, if all you're doing is just simple operations like a sum that you're seeing here, the performance difference is going to be constant. And the reason for that is if you look at the profile of my array.sum, it's 6 function calls. There's not a ton of layers of abstraction before we hit, right, the C level and we start performing a lot of heavy computation. Pandas have 6 function calls. Well, they have 121 function calls, right? And these are all at the Python level. So this is going to be quite expensive here. But we have to do so much extra overhead with any given pandas method. We have to do things with a block manager, allocate new space if it's needed. And you can actually see here, right, we're grabbing the block, we're checking the access number. We're doing so many different things just to make sure that this operation will succeed. Whereas NumPy is just going to say, hey, you know what? I'm just going to do the things I just perform the computation. If it works, if it doesn't, I'll leave that for you to check and figure out how to deal with later. But I'm just going to do the dot sum. Pandas does a lot of overhead when performing many operations, and so you should be wary of that. We also have this idea of our differences between NumPy ufuncs, which will always be fast, and pandas operations. And the story is this. I've been asked to compute pairwise distances between points in space. And if we're ever computing pairwise distances, the first thing that you might think of is, well, if I need to just take every value and compare it to every other value, well, I might just iterate over the values if I have a series of values, and then I'll just subtract each value from the original series, and then I'll store that, I'm kind of doing a split, apply, combine here, where I'm splitting, but just every single value. I'm applying, this subtraction operation, and then I'm putting them in a dictionary in order to combine them back into a data frame later. This isn't necessarily fast, but it's not necessarily slow either, We do have just 1,000 values here. And so I wouldn't hold my breath for this to stay fast if I had, say, 1 million or 10 million values. But what we can do is we can leverage index alignment instead of relying on explicit Python iteration. And so here, I'm going to create a multi-index that's the Cartesian product of just both my indices, just like this. And then I can use .reindex to rely on some alignments, not at the Python level. And what I can do is by specifying level 0 and level 1 here on the right-hand side, I'm actually creating the Cartesian product of both of these series, one against the other. This is very similar, if I were to do a series.join or a self-join, with a cross product. This is the exact same thing, but this is how pandas would approach it using index alignment. And we can see that this operation ends up being much faster because I'm not having to recompute or combine all these elements back together, and ends up being that this stack operation is going to be a little expensive too, just to coerce our data to a single series with a multi-index. But you can see that I can use index alignment to actually speed up my computations here. The one thing that I want to share with you, never forget about NumPy ufuncs. They have a lot of useful attributes. Specifically, if I want to get the Cartesian product of any two arrays, I can use the .outer methods attached to the NumPy ufuncs. And so all NumPy ufuncs have this, .outer, where they have a .inner, as well as a couple of other methods attached, like expanding to them. And so I can get the outer product or the outer subtraction of my pandas series against itself. And now I hope you're looking at this and you're saying, oh, you're calling 2 NumPy. Isn't that expensive? Well, we've talked about how series are just backed by NumPy and D arrays, especially for the integer data types or for the numeric data types. This is often a zero cost transformation to go from a single pandas series into a NumPy and D array. That's not always the case. There are some nuances, so we'll talk about that. But by using this outer product and then reshaping, I can actually reconstitute the original Cartesian product. And you can see I squeak out just a little bit of extra performance. While it's not going to be incredibly better, than we saw with the index alignment, we can use NumPy just for a little bit of extra speed in our pandas operations. In order to predict whether something's going to be fast in NumPy, we often resort to the use of views versus copies. Copies are going to be slow, because we're copying data around. Views are cheap. Things like reshaping or things like altering the data type or manipulating the strides are going to be cheap. Pandas does not have reliable view and copy rules. So it's going to be hard to predict performance, primarily when it comes to memory usage and memory consumption. Pandas will be making copies all over the place. Now, if I perform a promotion, and I'll share with you what that means. Promotion is when I say I have some arbitrary values here. They have some numeric values in this case, I have a series and it's an Int64 data type. And I, for some reason, maybe I'm not intending to do this, or maybe I am intending to do this, but I assign the value A to it. Automatic promotion will find the least common denominator, the most common data type that all of these can share in order to fit into a single array. And that brings me back to that object D type, which is going to be slow. And so you should always take care of actually implementing or taking care to check your data types before you insert or append or add or change items. Things like this can actually perform a fairly expensive transformation. If I go into NumPy and grab the NaN value, if I perform this s.fillNA with a 0, well, we stay, right, we get that float data type because this is being forced to a float here, accidental type promotion because NaN only supports floats or floats only supports NaN. But if I were to fill this with an A, right, I'm not explicitly, right, assigning an A into here. Maybe I just want to represent, right, maybe I want to use a string NA. That drops me into that object data type, which will be slow. Now, I did share with you that NumPy will try and use zero copying mechanisms, meaning that a pandas data frame and a NumPy and D array can share the same underlying array on its backend. And we can actually see this. If I create a NumPy and D array with 500 rows and 20 columns, and I convert that to a data frame just using the data frame constructor, I can use NumPy shares memory to check whether these things share memory or not. And I can even go ahead, I'll get rid of this portion of the code here. We can see that they do, in fact, share memory. Now, all it takes is the addition of one column for them to not share memory anymore. You can think this one column might not be triggering a new block allocation or anything like that, but it is going to add, right, an apparent column onto the underlying, onto the backed ND array. Even if I try and re-slice out the original, right, 20 columns in this case, well, we end up still finding an array that does not share memory. This is not to say that nothing behind or supporting this pandas data frame is based on that same NumPy and D array. I can actually go into the block manager and grab that 0th block, which is going to be that original 2D array that I implemented, grab the NumPy and D array backing that, and we see that it still exists, it still shares memory, and so pandas is trying its absolute best to not make copies, but in the end, pandas will make a lot of copies. So you should be aware that pandas is going to be copying your data left and right, especially when it comes to adding or removing data, performing filters, or very importantly, right, promoting items. So your fill and A, your replaces, and your changes with .lock. I will say this though, very, very recently, pandas has, I believe, approved PDEP, I want to say it's 29, that's the pandas enhancement proposal, and they will actually start releasing a warning in later versions of pandas 2.0 if you are going to be promoting, accidentally promoting, right, via .lock, fill and A, or replace. And they are anticipating in pandas 3, which they're actually expecting, I think, a little over a year, that they will actually raise an error, and this will no longer be an allowed operation because it introduces so many silent mistakes that are hard to catch.